So for this video, I'm just going to quickly go over the PowerPoint on weathering. And so when we talk about sedimentary rocks, there's a couple different classes of sedimentary rocks that we talk about. Clastic is a term that we use to describe fragments or pieces of pre-existing rock. And when those pieces are broken down and transported and then deposited somewhere, they can be turned into a rock, which we'll call sedimentary rock. And those are clastic because they're made of pieces of other rocks. There are also some chemical and biological rocks. When we talk about weathering, because we need to understand the process of creating those pieces so that we can get our lovely sedimentary rocks. So that's where we're going to go kind of real quick to just kind of run through some stuff for that. So what we see here, if I can get this thing to boogie for us. So remember, we're going through all the rocks. We've done kind of the igneous rocks. We've done intrusive, extrusive. We're heading up to this weathering process. And now remember, the weathering can be, we can weather igneous rocks that are exposed at the surface. We can weather metamorphic rocks that are exposed at the surface. And we can even weather pre-existing sedimentary rocks that are exposed at the surface. So anything that's at the surface is fair game to weather and then move that material somewhere so that we can deposit it and turn it into a sedimentary rock. And so that's kind of where we're going. So some kind of terminology. So when we talk about weathering in geology, it's different from erosion. So weathering is the breaking down of the rocks in place, and there's two ways we can do that. One group we're going to call mechanical, and that's kind of like a physical breaking down. If I took my rock hammer out to the field and I smashed it on a rock and it broke into pieces, that's a mechanical process that I'm breaking the rock up with. Chemically, I could pour some chemical on there, some acid, and it would actually eat away at the rock, break some of the bonds, and allow some of those pieces to be mobile. So we can chemically decompose the rocks also. Once they are in pieces, then erosion is the process of moving them, taking them from where they originally sit and transporting them, usually through wind or water, downslope due to gravity, and then deposited somewhere in a low-lying area. They build up and they form layers, they get buried, compacted, cemented, and can be turned into sedimentary rocks. So what we see with this idea of mechanical weathering and with chemical weathering is they kind of work hand in hand, because if you look at the little box on the left there, we have this 1x1 cube, and it is being attacked physically and chemically. But for my chemical processes, I only have that surface that it can touch. And so as I mechanically break my rock, I increase the surface area. So now the chemical process can attack more of the large rock or outcrop and start to break it down. And then of course that exposes more surfaces. And so as we make smaller and smaller pieces, we can increase kind of this weathering process, because now we have this tandem of mechanical weathering and chemical weathering kind of being very efficient as they work together. So that's kind of all that little diagram is trying to illustrate to you. And then I'm going to run through just a few of the mechanical weathering processes. So this idea of freeze-thaw or frost action is the idea that when water freezes, it actually expands. And so in, majority of the places on Earth, there is water, and potentially we can get that water to freeze depending on the seasons. And so what happens is water actually moves through the joints of the rocks, and then it freezes and it expands. And so we don't have this initial, like, as soon as it freezes, the rock breaks into 20,000 pieces. It's this idea that, remember, time is on our side in geology. We can have this freeze-thaw occur for years, and then it occurs for thousands of years and 10,000 years. And the idea of this expansion of the ice in a fracture stresses out the rocks. It puts stress on the rock. And so over time it weakens, and then finally it can fail, and that rock can crack and make that crack larger. Then I can get more water in it, then it expands even more and more stress, and the rock can crack. It's kind of like, like a paper clip. I bend it once, it doesn't snap instantaneously. If I bend it back, still hasn't broken. I keep bending it, and over time it weakens the material, and finally it can break. So it's kind of this idea of frost action. So whenever you have water and temperatures that can get below freezing, we have this process, and it drives a lot of this mechanical weathering that we see. And so a lot of times we have the material, then it gets moved down slope into this, what we're going to call Talus Slope, is just the loose material at the base of a cliff. And potentially if there was a river that moved through here, then that could take that material and transport it to a low-lying area. Now, if this is the final place where all these pieces are, we could bury these and we could turn these into a rock, and the rocks would look very differently. And we'll use the properties of the rock and try and interpret the depositional environment, which is kind of the goal, right? We want to be able to read the rocks. They're telling me a story. Is the story that they fell from a steep cliff, it didn't go very far, and they represent like a landslide? Or did they travel for hundreds and hundreds of miles and they're deposited in a delta that goes into an ocean or a river? Is telling me that story, right? I want to pick that up from the properties, or the kind of the properties of the rock, sedimentary rock. What? Okay. So another thing that can happen, so okay, here in Arizona, we don't get a lot of freezing going on, at least down in the valley. So we also have this idea of thermal expansion and contraction. And this property kind of comes into play here because we have such big swings in temperature. So the idea would be that we have certain rocks, and let's say we have an igneous rock that is crystalline and it's made of lots of different minerals. Well, each one of those minerals has different properties. And as I heat the rock, the minerals will expand a little bit because they're getting hot. And then as it cools, they'll shrink a little bit. But their rates aren't the same because they're made of different stuff. And so as these minerals try to increase in size and decrease in size, they put pressure on the contacts between the crystals. And then same thing over thousands of these, freeze-thaw or thermal expansion contraction events, we get stress along those mineral grains, and we can get a fracture or a crack, and then we can make that bigger and bigger and bigger. We get a little water, and then we can move that stuff. And so it's a process that can also cause these stress along these mineral grains and cause cracks and fractures in the rock, a way to mechanically weather the rock. And then we also have this process called exfoliation, but if you like, pressure release is good. A lot of times it's associated with igneous rocks. So remember, our intrusive igneous rocks, like this batholith here, form deep inside the earth with several kilometers of rock sitting on top of them. That's a lot of stress and pressure here. As we uplift this area and strip off the material on top, we're releasing the pressure. And so this batholith, the rocks and materials in here, want to expand a little bit. And so that expansion can cause fractures to occur. And once again, it doesn't happen instantaneously. Number one, we're removing the material on top slowly. But as that rock gets less and less stress being applied to, less pressure, it's expanding, but it won't instantly just break into a million pieces because the rock is strong. And so over time, we'll get fractures and cracks developing as the rocks just can't take that change in pressure anymore. So I'm going to show you really fast this video, which is one of my favorites. But if you happen to ever see this, so here these people are looking at, I know it's hard to see, but this is actually an igneous rock, kind of like it's probably a granite or a diorite of some kind. And so they're hiking in the Sierras, and they hear some weird noises and see some weird things. So okay. Ho 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 ho. Oh. Okay, so it's not Santa, but it's he's hearing cracking coming from the ground. And you actually saw a little piece kind of pop up there, but they're trying to figure out what's happening as they're hiking along.
All the way down. This whole seam now is active again. Lots of activity down below. It's still lifting. Did you see that? It just popped right up.
I felt that way.
Little piece flew into the air.
Yep. Okay, so what the heck just happened? Right, so that's the exfoliation process. This idea that this rock has been under stress for thousands and tens of thousands of years, and finally it couldn't take it anymore, and it fractured or broke there from this release of pressure because this thing used to be buried very deeply. So, not an earthquake, this is just a mechanical weathering process. All right, so let's go back to our lovely PowerPoint. So that's the mechanical process. There's a couple more. So we see that just some more. These are more related to heat. Sometimes after fires, you see boulders like this that have broken. We also get organisms that break the rocks mechanically. So burrowing creatures and roots that move into rocks. We see this here in Arizona where there's not a lot of soils for sure. And so even though you think, well, it's just a little tree root, but there's thousands and thousands and thousands of trees, and over time they can do some damage and break the rocks into smaller pieces. All right, so what else we got? We already did this, so I'm going to cruise through that. So really what we see for the second part, chemical weathering process, we're not going to focus on a bunch, but the main one is this idea that certain rocks can be chemically altered, and what happens is the water that just falls from the sky is slightly acidic. So we think it's just kind of, this lovely water, which it is for us. But what happens over time is some of the minerals and rocks can start to dissolve and break down. And of course, the most common one that we see this happen with is limestone. And so carbonic acid can form naturally. And so we get this water, the CO2, and the water can form this kind of acid. And so it can cause certain minerals to react, like feldspars that are very common in igneous rocks. It can also affect limestones, things like that. So calcite is the mineral, limestone is the rock, the sedimentary rock. Now, as a geologist, we use hydrochloric acid in the field or in lab. It's very dilute, so it can't, dissolve your whole body. But when you place it on a rock that's made of calcite, and in sedimentary rocks that would be a limestone, it actually will fizz a little bit because it's reacting and is starting to dissolve some of the material. And so in the real world, when we see limestones, they can be altered by just rainwater over long periods of time. So on the surface, they can get pitted. Large areas of limestone can actually dissolve away and form caves. So if you've been to Kartchner Caverns or Mammoth Caves, a lot of those systems are formed from the dissolution of limestone over long periods of time as either surface or groundwater has moved through those rocks and slowly dissolved them. And so the other thing we get is, we won't talk too much about hydrolysis. It's still that water's interacting with the minerals and breaking the mineral grains there, so don't worry too much about that. It has some ideas about how we get to clays and things like that. Another process, just to bring it up because you see it here in Arizona. If you've been to Sedona, the rocks are red. And a lot of that red color is from hematite, a mineral that is formed from the weathering of pyroxenes, which are minerals that we sometimes see in igneous rocks. And they react to oxygen. The iron breaks out and reacts to oxygen. We get Fe2O3, which is hematite, and it's very red in color, and that forms some of the cements that hold the sand grains together, and it gives it a red appearance. So really the rocks are rusting, they're oxidizing, and that's what gives it its red color. And so when we go through weathering processes, just some general kind of graphs here just showing you things that are the most stable, that take a long time to break down, and things that break down very easily. So quartz is up here. And remember, quartz is very common in igneous rocks and granites, and this is why lots of sand that we see is made of quartz. Quartz sands are common because quartz does not weather very easily, so all the other minerals fall out. It's very resistant. When it gets traveled long distance, it doesn't break down. And so by the time it gets to the coastline, it's these small little fragments of quartz. So we get lots of quartz sands at the beaches. These other minerals here that are easily dissolved in, let's say, rainwater, like calcite or evaporites, right? We know that it's like a salt. It's easily dissolved in water. Those don't last very long. All right, so that's probably all you need to kind of worry about for the weathering part of the sedimentary rocks, and then I'll make a couple little videos about the rocks themselves.